You're listening to China Manufacturing Decoded from the Sofeast Group.
Hello everybody, this week we are talking about the 5 main uses of prototyping equipment. And by this we're thinking of 3D printers, everybody's kind of thinking about that. A lot of people are using also CNC milling, sometimes CNC lathe. People are also using the sort of small versions of PCBA equipment for assembly of PCB boards, and so on and so forth. And of course, it includes spray painting and a lot of other types of surface treatments. And there's virtually no limit. There's a lot of things that could be put in the category of prototyping equipment, right? So why is it important for not only design houses, but also manufacturing companies to have some prototyping equipment? And why also maybe sometimes the companies that develop their products, even if they are not going to manufacture them, if they do some of the design in-house, why they would benefit from having some prototyping equipment. And today to discuss this, I am with Paul Adams, who is the head of our new product development team. How are you doing, Paul?
Hi, welcome. I'm doing very well. Thank you, René. Good to be back on the podcast and talking to you and about a very interesting subject today.
I think we do. Yes. So first, let's sort of, take a few steps back and say, first, what is prototyping equipment versus production equipment, right? And then we'll discuss why it's so important for people to have this type of equipment, and then we can break down, okay, there's we counted 5 main topics, 5 main types of uses of prototyping equipment. Obviously, it's mostly in product development, right? But not only that. Okay, the first, talking about prototyping equipment, when we look at, some kind of high-speed machine, highly automated machinery, usually that's production equipment. When we look at things that are good for making, let's say, between 1 and 50, maybe up to 100 pieces, takes a longer time to program. It's a bit more manual. It's slower. But anyway, you don't have to go through 1 million pieces, right? It's just, again, maybe 10 pieces, 50 pieces. That's the main distinction that I make in my head between prototyping and, high volume production or mass production, however people call it. Does that make sense? What do you think?
Yeah, it does. Yeah, I was thinking something the same. So if you've got, take a milling machine, for example, now for production, in my mind, I've got a very, very different image for a production milling machine versus a milling machine that could be used for a prototype. Now, for a production, this is going to be a highly automated CNC 5-axis machining center, that is utilized 24/7, and it's like pumping out production items and really sweating that asset. Whereas you've got your milling machine that is used for your initial prototypes. That's going to be more of a manual device, more of an NC as opposed to a CNC. In other words, numerically controlled. So you've got very tight control over the position of bed, and you've got some very good control over what you're machining. But that could be sitting there very, very underutilized. In other words, it's there to produce that very low volume, very specialized one-off to start with prototype material. So you're right. It's very much the same machine in effect, but on different levels of the scale, and utilization is chalk and cheese. High utilization for high automation for production, whereas you've got the more of a manual aspect type of thing coming in for the manual lathe milling machine. So just trying to portray a visualization of what we're trying to talk about here, from a milling machine. So,
typically, because we have CNC machines that are for, let's say, more production or, or for making the tooling for plastic injection molding and things like that. So these are big machining centers, right?
Yeah.
And they are programmed and so on. Okay. And then when we go in the prototype lab, we have some small CNC machines that are more manual in their setup. So they are much smaller, right? First. And the person has to sort of rotate a wheel to position things, right? However, once it's positioned, once it's set, it is still pretty accurate in what it's doing, right?
Yeah, I was going to say, so this is a key thing, so when we're producing prototypes, we need to make sure, depending on what the prototype is for, clearly, which we can touch on in a minute, the accuracy is still a very important aspect. So, and this is why we tend to go with not necessarily 100% manual, like I trained on when I was doing my apprentice many, many years ago. Let's face it.
That's all.
More of more of an NC, more of a pneumatically controlled. So you've got that even though you're moving the bed and moving the position by hand, you've still got the numerical control with respect to that. So you're moving to the 0.01 millimeters accuracy, because you've got that numerical control display telling you exactly where you are. So you've still got the accuracy, but you just don't have the automation or the high speed throughput that you would for production.
Right. And then when people hear about prototyping, they think 3D printing very often, right? And 3D printing has been making a lot of progress, right? It's really getting better by leaps and bounds. So I think within the next 10, 15 years, it might become mainstream for certain types of mass production, of certain components, right? When we look at, say, consumer electronics, or even B2B electronics, that doesn't go into like a space shuttle or something like that, right? We're talking like more mainstream products. 3D printing is nearly nowhere to be seen in mass production, right? All the parts are made, they are cast, they are injection molded, things like that, right? So 3D printing is still predominantly a prototyping technique in our world, right?
In general, so broad brush terms, correct. Yeah, that there are, as you say, very unique speciality areas where you're using very special materials for 3D printing metal that can be used in a certain application, but we're not talking about that. We're talking about general consumer products. Very rarely would you be able to take something apart. Take your average computer, for example. If you took that apart, you wouldn't see any 3D printing inside of that. Everything's like machined, injection molded, cast, or there's a lot of sort of PCB assemblies in there. So everything's like mass production, mass produced at scale.
Right. And then, another topic I wanted to touch on briefly before we go into the 5 main uses of prototyping equipment is why, it's so beneficial for a company to have some prototyping equipment in-house. I feel that when you have the design engineers, interacting with prototyping equipment and, sort of testing the limits of it and so on, it makes them more aware of the constraints in mass production. Now, it may not be the same process at all. Like you 3D print out of the plastic enclosure, and then you're going later to make tooling to injection mold it, for example. Quite different and quite tricky. If you use 3D printing, you really have no idea about the constraints of, molding it together and demolding it and all these things. However, for example, for metal machining or, machining of anything, because it's often used on plastic too. I feel that really it helps them understand the limitations of the equipment already, and it makes for a better design. Does that make sense?
It does, yeah. One of the things that we focus on is DFM, design for manufacture. Okay, and going back to what you were saying there, and it is allowing the designers and the developers to actually use and create early stage prototypes will allow them to understand the features that can be used in production to make life easier from the assembly point of view, as well as disassembly in some cases. So, it's like we give a lot of credit to the designers around the world with respect to how clever they are and coming up with the unique designs to put everything together. But, you've got to think about how they actually created that and how they would test that. And a lot of it is trial and error. And trial and error can be expensive if you are saying, okay, we've designed it, let's go straight to tooling because I believe my product design is correct. And it's a mistake. That's an expensive mistake. So if you're looking at fast iterations and learning along the way, this is where the designers come up with a lot of improvements over their time in their career with respect to, I tried that didn't work. Tried that through a rapid prototype that I tested on CNC plastic machine part, for example, because I know that an SLA or an SLS, is more brittle. As a snap fit, for example, it doesn't work particularly well, but a CNC machine part does work. And this particular feature or that design is the way forward because they've tested it. They've known that and they've got that advantage by being around the rapid prototyping kit and the different tools and processes that are available for prototyping. That's a huge advantage for any designer. So having that capability in-house does allow for better training, better knowledge, and better understanding of all of these features, functions. Ultimately, they're going to produce a product that is better for assembly in the long run.
Right. Yeah, it makes a lot of sense. Okay, so let's go into the beef of this episode. Basically, you have prototyping equipment that allows you to design a part, often from scratch, and then make it a reality, right? Within the constraints, you already have to design for the ability of your prototyping equipment first, right? Obviously, if you, I don't know, even 3D printing has a lot of limitations. If you have some parts, some aspects of the geography of the part that are sort of overhanging, nothing to support them and everything, it's often an issue. Okay, different from, there's different technologies even within 3D printing. So that's the case for some of them, not for others, right? So, but the key idea is that you can custom design a part and you can make it a reality, right? So we thought about it and we made a list of five types of users. And the first one is to start to make functional prototypes, right? And at the very beginning, it might be what people call a proof of concept prototype. Let's just hack something together. Doesn't, look nice, doesn't do all the functions that would be that a product that we might, that we put on the market would have to do. But it does one or two things sort of well enough that we can already validate, whether this product made sort of this way with that concept will actually solve that problem, right? And sometimes people write, product requirement documents and maybe they work with a industrial designer or just like mechanical designer. And then they say, oh yeah, it would work like this. And it would be, especially for intricate mechanical products where you say, well, you would have a gear that would do this and you would have whatever lever that would do that and so on. And it's all theoretical, right? But until you actually get it to work and you can observe how it works and you can observe, okay, we have a problem here. We need to solve that in the design, before we can go very far on this project, right? So the earlier you can make something tangible, the earlier you get this feedback and the earlier you can basically improve your design, make it, what we call that feasibility study, right? In the NPI process. And the feasibility studies objective is to make sure that you're actually developing a product that is a real product, right? It's not just a concept, a theoretical concept, but you need to check, okay, rubber meets the road, and how do things behave, right? Do we have something that's going to work, or like, okay, there's no way it works like this, back to the drawing board, and let's go with another concept that will then again have to validate, through prototyping, right? Well, proto testing, right? Prototyping, testing, and maybe doing some iterations, adjusting the design, remaking one or a few prototypes and testing them, and so on. Does that sound like a good process? What do you think?
Yeah, this is perfect. And more often than not, it's not just the complete product that we're looking at. It could be a small section of design. Take, for example, a hinged area within an intricate part of the design that is, I'm not sure whether it's going to work. So what was really useful is to focus on just that particular area, say a living hinge, for example. Yeah, it's like various different materials work really well for a living hinge, polypropylene being one of them. But we wouldn't want to build the whole product. We could just prototype that small area, right? And that would give us the insight with respect to, does that mechanism work, for example, for this particular product or the design? Now, if, and again, this is where we need to be really careful with respect to going back to the equipment that is used to create the prototype. Now, we know, or we should know, that certain materials used in SLA or SLS are not suitable for a living hinge, for example, because it's too brittle. So we're trying to use a prototype to hinge. We need to work out what process we are going to use. In other words, what equipment from our list of prototyping equipment we're going to utilize to, just have that small section of the design validated. In other words, feasibility study, make sure it's feasible to go forward. And something like this, I would choose a CNC plastic. Mm-hmm. So again, looking at how to utilize the equipment that we know that we can use for prototyping and match that with the actual environment and situation that we're trying to validate at that point.
Absolutely.
That makes sense?
That makes sense. Okay. Yeah, totally. So when you start to design a new product and it has to interact with, users and the aesthetics and the touch and feel and the whole user experience is important. There's also another track, right? So there's let's say, pure engineering sort of, is it going to work? How to make it work in the most efficient way, et cetera, how to reach the performance requirement and so on. There's also another track, which is more design related, right? And you start to work on what people call look-like prototypes, versus work-like prototype, which is what we just discussed before, right? Functional. This is, look-like prototypes, visually appealing prototypes, right? But it's not just visually. It's also, what kind of materials, how does the user actually feel, when seeing the product, when, touching the product and so on, right? And so there's a much stronger focus on the surface appearance of the product, right? But it's not just about the surface appearance. If you have several parts that need to fit together with a small gap between them, or no gap at all, if that exists, then you need also to control the dimensions carefully in this case. So it's a little bit trickier than just, getting it to look nice on the outside, right? Because you might, and we discussed this before actually on a recent episode, but a typical problem is you want to have, let's say, a plastic part in a certain color. And of course, in mass production, you have your tooling, you do injection molding, you mix the pigments in the polymer when you put it in the hopper of the machine and so on, or before you put it in the hopper. you mix it so you have the right color coming like right out of the gate, right? And there's no need to paint it right now. Of course, even in mass production, a lot of products have surface treatment on the plastic, right? They might want it to look a bit more metallic, for example, with PVD coating. They might even, I don't know, need some overmolding. Okay, there's a lot of complex things that can happen in mass production. But for prototyping, it's very, very common, much more common in mass production, to paint plastic parts, right? So plastic parts coming out typically of 3D printing, right? You 3D print, then you polish, so you don't see the sort of stratas that are typical of something coming out of a 3D printer. It's not very smooth. So you polish a little bit, then you paint, and then you're like, well, because of the color of the 3D printed material, because of the thickness of the paint layer, because of this and that, I'm not reaching the exact required color. So maybe I'm going to put an extra layer of paint or something, right? If you really need the prototypes to look nice, you get to match, the desired color tone pretty accurately, right? But then it's very hard to control the amount of paint, the thickness. And then as I mentioned just before, if there's something like another part that fits into this part or something, if you are a bit off by a quarter of a millimeter or half a millimeter, no, maybe not that much, but even a quarter of a millimeter, you might have like a big gaping gap that's pretty ugly, or it might be hard to adjust things together, and then suddenly like it doesn't close neatly, So if you really want to get that kind of prototype right, for one nice prototype that will come out, that will be approved, well, depending on the standard of the buyer, of course, you might have to make 5 prototypes or 10 prototypes, or even more than that, right? So the standard that has to be reached is really critical. It has to be defined in advance. We discussed this in a recent episode. Does that make sense?
Yeah, it does. And this is a key point to remember, that anybody who's looking for the perfect prototype needs to reset their expectations with respect to what they're actually asking for and what they're going to get. We had a particular case study internally with one of our customers on that. And I think that's what sort of spurred the sort of the previous episode and discussion there. But it was a prototype that was going to be used for, it was going to go into a video shoot. And that video shoot was going to be uploaded onto the website with respect to installation and maybe some advertising aspects. And that the prototype needs to be visually perfect. Now, the perfect inverted commas, the air inverted commas I'm doing here is very, very difficult to achieve because of the things that you mentioned there. It's like you've got a 3D printed product coming off. The accuracy is not going to be as good as injection molded part for starters. Then we need to add the paint coat. Now, coating is additional layers of thickness. That thickness, again, adjusts the overall dimensions. And as you say, when you're trying to slide 2 parts together, it's either going to be too loose or too tight. And this is particularly a potential problem. So again, we need to look back at the equipment used in order to provide the best prototype for the situation that is going to be used in. Now, if we're talking about visually appealing prototypes, 3D, it depends on the product. Okay. It's like, again, inverted commas here, depending on what the product is. You can get away with some of the 3D printed products that are, a little bit of post-printing polishing and sanding and then painting. It's going to be pretty good. Pretty good. But in some cases where we've got, 2 or 3 components being assembled together and each of the match lines needs to be perfect, it's going to be very, very difficult to actually achieve that with a prototype, with I've gone away from using the term perfect prototype. I've gone into using as good as we can get prototype, because
Right.
of these,
Right.
you know,
Yeah, so
and,
true.
and
Yes.
and it is the case. It is the case. But yeah, you have to take into consideration what the prototype is, how it's being used, and what is physically capable from a prototype process. We went away from 3D printing in this particular case study, and we went into full CNC machines, big block of plastic, a lot of waste material, but the finish was a lot better. It was closer to production intent than a 3D printed product could ever been. Now, we still had to go through painting and post finishing, but the overall finish, once we finished this process, that looked pretty good. That looked pretty good. And the customer's ultimately happy with what we got here. Now, when we're talking about visually appealing, so what comes to my mind is the CF product, or the color finish material. Some cases, the material has to be ignored. Sometimes the texture or the finishing, it can't quite achieve what we're going to be looking at in production because of the process, but certainly the color. All of these things need to be added with care, understanding, and expectation when it comes to visually appearing. This is probably one of the most difficult things to put forward if the end use is critical. For example, this is going to be used in front of the camera for marketing purposes. Therefore, it needs to be, visually appealing at a close up, zoomed aspects. You need to be very, very careful on that point. If you're looking for, some photographs to put onto a website or something like this, probably okay. Probably okay. So set your expectations, talk to the supplier, and making sure you're having that very, very clear understanding of what is potentially achievable from a prototype in this aspect.
Right.
That would be my,
You mentioned,
yeah.
you said CFM. I think people usually say CMF, right? Color, material, and finishes.
Yes.
Yeah.
Color material.
Yeah. Usually this is typically what an industrial designer would help define, right? And then you get to work on, okay, let's try to make something that looks close to this. But again, it's not going to be exactly the same as on, something coming out of Photoshop or something, right? That's the key idea here.
Yeah. And again, there's different, depending on what the product is. Yeah. There's different equipment that can be used that will give you a lot better result than something else. And again, that conversation should be had with the design team to see what the expectations are from the product, such that the equipment or the process can be matched in order to provide the best possible result.
Yeah, makes sense. Okay, so we have work-like prototype, functional prototype, and then look-like prototype or visually appealing prototype. And then at one point, when you're getting into a bit further into the process, you try to put together a look-like and work-like prototype, right? So the outside has to be as close as possible to what the industrial designer has in mind, but internally, or not just internally, like the buttons, the display, everything, like it's got to work, right? So this is another one, but it's a bit of what we just discussed before. So we're not going to go deeper into this. Another reason to use prototyping equipment is to try to make prototypes that can be put through stress testing. So let's say your look-like prototype is going to have to be 3D printed, but then you start to look into, okay, for example, drop test, it's just one of these dumb kind of tests. If it falls from a certain height, and obviously it has to sort of replicate the use case and so on, is it going to break? That is obviously that's a reliability and durability topic, because you don't want your product to fall and break too easily. And we discussed this, I think, with Andrew just a few episodes ago, right? About what in the mobile phone industry, where he has a lot of experience, what people are actually accepting, versus what they could not accept when Nokia was the big brand and before the iPhone, right? So, people have expectations. You get to make sure you match these expectations. So that's on the reliability side. But on the compliance side, if your product has, like live wires inside and so on, actually the enclosure should not break too easily. It is a safety element. It's a safeguard, right? It's not just about live wires. If there's something that gets very hot inside the product or anything like that. So the enclosure is a safeguard, and all of these IEC standards about electrical home appliances and so on, even a lot of IT equipment, office equipment, the product has to pass a certain type of drop test. If the enclosure breaks too easily, then it fails, because the enclosure cannot be counted on as a safeguard, right? That's just a dumb, simple example that a lot of people can understand. So how to actually make sure, if you have a doubt, you're not going to take something 3D printed and drop it. No. It's got to be a prototype that first, it's a little bit advanced. So there's all the same components as the final product, right? It may not be fully functional or functional at all if it's for reasons that will not impact the performance in the drop test. That's probably fine, at least for reliability, right? For compliance, talk to the labs. They might have different opinions, okay, depending on their estimate of criticality here, and based on the risk analysis, basically. So how are you going to make the enclosure, properly? Well, if it's pre-tooling, you don't have tooling yet. One way people have been doing this is with sort of silicone molds, or, vacuum casting molds, or, typically in urethane casting, often people call it. But that is something that can only be used if the part can be demolded easily. All right. So we've been looking for some other ways to do that, and something we're experimenting. We're quite excited these days. And you were working on this even yesterday, is what they call freeform injection molding, right? By Nexus 3D. So we have the 3D printer with 3D printing a mold, and then the part of the mold, typically the core, that would be stuck because it cannot be demolded, if necessary, can be dissolved away in 24 hours. So you can really do injection molding. In this case, we're talking about plastic, but it could also be silicone or some other materials with real ABS, real PP, and so on, right? So quite different from a lot of prototyping applications. Here it's with a real production intent material. And you can, apart from texture and some small details that would take more work with that technology, it seems relatively straightforward to actually get, parts with the same geometry and the same physical properties as you would have in mass production when it's injection molded at high pressure, in the typical plastic workshop, right? So that's another type of prototype, and you need to think sometimes of a different type of equipment and technology, as I mentioned. Anything that you have to add to that, or?
Well, with respect to freeform injection molding, I think that's going to be a separate topic, podcast on this one, because that's a very exciting new technology that we're looking at. But just to touch on it quickly, what that is going to allow and provide is exactly what you said. up until now, we've been talking about various different materials that can be used for prototyping, various different machinery or equipment that can be used in order to produce your prototype. And a lot of the times there are limitations with what can be produced and how it can perform. Most of what we've been talking about, if we're talking about CNC machining pieces of plastic in order to get the rough design or close as we can get to design for production, that's okay, but it's not actually going to be structurally the same as an injection molded part. Okay, because it's a block of material that has different properties than one that's been injected. It's the crystalline structure within the plastic part itself is totally different. Okay, so that's one thing. Now, with this freeform injection molding, that does allow injection molded parts with 3D printed tools. Okay, so let me say that again. Is plastic injected parts with 3D printed tools. Now, that is a sentence that I've never said before. Okay, those two have never come together up until this point. Okay,
Well, they were
so because
actually, I did a bit of research. They're not the first ones or the only ones to do that. A lot of people have been trying to do that, and actually for molding silicon prototypes, it's relatively common. However, here we have two big advantages with this technology, is that the mold itself can dissolve, and that solves a lot of headaches. That really opens the door to a lot of new applications, right? And the other one is that it's really, actually, I think it's also possible with some other 3D printed tools, but you can really use like real ABS or real whatever you want, PP and ABS and so on, but the real breakthrough here is that it's dissolvable, right?
Yes. Yeah. Well, the injection, the tooling that we're 3D printing, that is a resin that can be that can withstand the high pressures and temperatures of injection molding. Once it's injection molded, there are no need for complex sliders or ejection points or anything like this. You basically dissolve that 3D printed tool, leaving and exposing the injected part. Okay. Now, this has huge advantages, massive advantages when you're going through not just stress testing, but stress testing is a key aspect here because you're able to test the actual polymer that is going to be used for production. Okay, this is a really, really important point here. But it also allows on the early stages, going back 10, 15 minutes, whatever, we're talking about the designers getting better at their job from a design point of view, that allows them to, what this process allows them to do is go through very rapid changes with production intent material, without going into expensive tooling. Okay, so we're testing a product. Your tool maker is going to say, yeah, if you want to test that, no problems. Minimum you're going to be spending a couple of $1,000s to get the steel tool up and running, or you can spend $100 on a 3D printed tool, for example. Huge advantage, both at the front end and where we're talking now about stress testing the product. Okay, drop testing a 3D printed part is not going to give you the result that you're looking for. It certainly will not pass any certification if we send it out to a third-party lab,
right?
Which they're testing for. It's just not going to cut it. It's not the right material. However, this freeform injection molding, in other words, injection molding polymer that you're going to use for production with this 3D printed tooling, is going to solve all your problems. You will be able to submit parts for reliability, certification, whatever you want, without steel tooling. That's the key.
Yeah, of course. When you go into mass production, it's going to be different. One more thing is the speed at which you can do iterations. You can design and 3D print an injection mold, in the same day. And then if you haven't made big efforts on demolding, with whatever pins and inserts and whatever. You just dissolve the core. Takes you 24 hours with their equipment. And then, right after that, you check, and then you say, okay, let me adjust the design a bit like this. Okay, let's do a new iteration. So we're talking, 1 or 2 days per iteration cycle. We're not talking, however long it takes when you make the tooling and then you need to revise the tooling. It's pretty damn expensive, but it's also very time consuming.
It is, and if you compare that to sort of production tooling, we give the standard 30 days to T0, another potential 30 days for sort of final sign off. You're talking quite a chunk of time to get from, okay, we've got a CAD design here, let's get a plastic tool made, and we've got the plastic part at the end, versus we've got the CAD design finished. Okay, let's go. Okay, and the time starts ticking. You can go to printed, you can go to injection molding the same day, within hours, literally within hours. And as you're right, then you've got to go through that 24-hour dissolving process, and you've got the part on your hand. You find out you've got to make a small change, process starts again. You can have multiple iterative changes within a week, and you've got all these different parts in front of you. With the production polymer that's going to be used, this is a game changer. It really is.
Yeah, right.
Anyway, we'll save my excitement, Renard, for the next episode.
Yes.
It's real depth with respect to how this done, who can benefit from it, and how to do it.
Yeah, right. We'll talk more about this technology.
Yeah.
So these are the first 3 main uses of prototyping equipment. Number 4 is what people sometimes call a bridge production run. And I'm not going to cover this in depth because we'll have another episode a little bit later on that topic. But really the idea is that you develop a product that you want to sell to a big manufacturing company or utility or something like that. They want a pilot. They want 20 pieces, 50 pieces, and then you have a few potential customers like this. You want to put it in their hands as fast as possible. You don't want to go through, okay, let's make the tooling and let's do this and let's do that, right? You want very fast. Or you have some Kickstarter, backers maybe that say, well, you guys are really late, what's going on? And then they become very loud and dissatisfied. And how come, you said it would be 3 months. It's already 6 months, 9 months, because product development and DFM, and, there's a lot of problems that you need to solve. A lot of, design iteration you need to go through, issues you need to go around and so on. So people usually end up late, behind schedule. But what we see is that very often they have a lot of pressure to deliver to some early backers, right? And it might be, again, 50, 100, 200, maybe 500. Maybe they sold, I don't know, to a retailer already wants to have something going on. Maybe it's 1,000, 2,000, 5,000, usually it's not tens of thousands. Okay. But how do you do that? Actually, in some cases, it may make sense to use prototyping equipment. It's going to be a higher price per unit, higher cost per unit. But when you look at the full product, because not every part of the product has to be prototypable, right? A lot of them are standard off the shelf parts. It may still be okay. You may not make much margin, but you really need to deliver that. It's about maintaining trust, keeping your marketing and distribution channels active and so on, right? So it's not just about making margin, but very often people are okay to make this with near zero margin. Okay. But again, we'll talk about that in another episode. And then, and we call it bridge production. I mean, people call it bridge production because it's like a bridge to get people to wait a bit. Like, okay, we don't have the tooling yet, but we already have some products, sort of a shortcut, if you want, or a bridge, just like a bridge financing round, right? We're between round A and round B, and we're going to do a bridge, just to allow us to wait until round B, that's the idea. And then let's go directly to number 5. And I'm sure you have some experience on that you can share. It's to make, production tooling in in the widest meaning of production tooling. So we're talking about fixtures and jigs and things like that need to be put in place, for example, on an assembly line and so on. Also for logistics, when you move products around, it's nice often to make some nice dunnage. So dunnage is the fancy term for, how to say, maybe some pre-cut foam or maybe some thermoformed plastic sheet, sort of like blisters, plastic sheets with imaging like blisters, and then you can put them, one part here, one part here, one part here, one product, and you make sure that they don't get crushed, they don't get in contact with each other and so on. And this very often is done with prototyping equipment as well, right? I guess you've seen that multiple times, right?
Exactly. Yeah. So with here in Gillian, so on the shop floor, where we've got different products going down, everything has its unique shape. Everything has its unique way of being put together. And what we look at is, and everybody should be looking at this, is ease of assembly, ease of movement, and ease of travel between stations, and that between workstations as well as production line stations or different stations with respect to, you talked about, dunnage and making sure that you're protecting the products from one place to another. And that could be from goods in, all the way from goods inwards to quality out and being shipped out. Now, it's no good going into mass production for a one jig. It doesn't make any sense. It's just ludicrous to think like that. So what do you use? You use potentially the same equipment as what we've been talking about for producing prototypes. The sort of the small manual mill. Even when it comes to some of the pieces of equipment on the production line for orientation of various different products during assembly, we can 3D print, or a CNC machine or even SLS or SLA, a simple jig in order to hold something or present something to the operator in a certain orientation or fashion. So there's an awful lot of production tooling that is prototype tooling. Yeah. So jigs, fixtures are all made of the tools that are used for prototyping. We can walk down our production line and it's full of it, absolutely full of it.
Oh yeah.
And it's, and I like to think that we could utilize, and in fact, I've got one of the things that we're looking at the moment is I want to go back to the sort of freeform injection molding and sort of the 3D printer that we're using there. The sort of the build plate, as you take that out of the machine, it needs to be turned over after the wash station needs to be turned over and the parts being knocked off of the build plate. Now, the guys at Nexa 3D, they showed us this and they actually 3D printed a jig in order to put the build plate in. So they're 3D some fixtures in order to help them with that process itself. So,
right.
It's when we're, all of this have as a form and purpose, It's really cool.
Yeah, you even 3D print some let's say tools to help with the 3D printing process. That's what you're saying.
Right. Yeah, correct. It's and again, it's really thinking smart with respect to how best to actually do this. Do I CNC machine it? CNC machining obviously has a relatively high cost versus do I 3D print this, using a particular resin, which gives us the right properties in order to do, what we need to do. Now, if we're talking about jigs and fixtures for the production line, that's super, super important with respect to accuracy and affordability. We don't want to be spending hundreds of thousands of dollars on jigs and fixtures when there's no need to. Yeah. So again, that's thinking smart, thinking outside the box sometimes. Like we said, using the 3D printer in order to help with the 3D printing process itself. So we really need to think smart, clever, and utilize the equipment in order to provide a best solution where needed. Yeah, you're right. It's jigs and fixtures is a big thing.
Yeah.
Each product has its own set of unique jigs and fixtures
right.
in order to make the assembly process or, checking reliability, quality inspection in process, finished process. Everything has these, all the little jigs and fixtures, and every product has its own unique set of jigs and fixtures to go with it.
Absolutely. Absolutely.
Sometimes,
So
it depends on volume. Yeah, it depends on how many jigs and fixtures we need. We may need, half a dozen or 10 of the same thing, but we don't need to go to mass production. That's the good thing. We don't need thousands of these jigs and fixtures.
Totally. Yeah, totally. That's a big one. Yes. All right. Well, that was a nice overview. Yeah, I was thinking about this yesterday again. I was looking in a supermarket. They had a door open in the bakery area, and some of the nice supermarkets. I'm in France for this week, and some of the big supermarkets, they have a really nice bakery setup. And I was looking at all the equipment they have and everything, and that's mass production, right? And then I was thinking of all these bread making machines that were pretty hot. I don't know, 5-10 years ago. A lot of people were buying a little machine to put on their desktop in their kitchen, the kitchen top, I should say, to make their own bread. And then they kind of all stopped doing it, right? But this is basically people getting excited by, prototyping equipment, let's just make one at a time. It's going to be more manual. It's going to take longer. It's going to be a bit more messy, but I'm going to do it myself, and that's the same idea in a lot of hacker spaces around the world. Even some co-working spaces I see in Hong Kong, for example, have, an area with 3D printers and so on. It's pretty exciting for people. And again, very good at the early stages of a new product development to start to plan for what the product should look like, how it should work, and so on. Thanks a lot, Paul. So this was a pretty nice one. And thanks to the listeners, and you will hear from us again next week as usual.
Thanks again for listening to this podcast brought to you by the Sofeast Group. We're on a mission to provide you with everything you need to manufacture effectively in Asia, including inspections, auditing, new product development support, contract manufacturing, 3PL warehousing and fulfillment, and much, much more across Asia's key manufacturing areas. Visit us at sofeast.com, that's SOFEAST.com, to learn more and get help. If you've enjoyed the podcast today, please do rate, review and share, because it will really help others discover us too.